Well, here we are back at the sun using H-alpha light. Jim showed us this prominence earlier this morning. It is evolving. We're looking at it here with the same setup I showed you earlier, a dedicated solar telescope and a dedicated camera. And I'm at about 10 milliseconds this time, so 10/1000ths of a second, and just under halfway on the gain for those who like to know this. You remember Jim showed us that there was an arch. In Jim's image, it was the mirror image. It was the other way around. The arch is, in this case, the arch is now on the right-hand side of the prominence, and there was something he called a curtain on the left-hand side. That curtain is now becoming more of a pillar. The arch itself, you can still see through under the arch, through to the other side. Why is the sun white like this? Because with my camera, the dynamic range, which is the technical term for being able to see both bright things and dim things, isn't that brilliant. You'd have to have a more expensive camera for that. So I've had to increase the exposure time so that we can actually see the prominence, and that overexposes the sun. As Jim pointed out to us, there are all kinds of small bumps around the edge of the sun. If you move to the right of the main prominence, you can see a very small little bump there. It's undoubtedly some form of a prominence, but I'm not resolving it very well. But the important thing is you can see this arch. And this brings us back to the question that Jim was addressing about how does energy actually come out of the sun and into what's known as its corona, which is the outer atmosphere, which we can't see here because the sun is way too bright to allow us to see something as dim as the corona. You can only see coronas during a full eclipse. But the question is why is it that the corona is 1,000,000 degrees centigrade hot, whereas the chromosphere, which is what we're looking at here, is something in the order of 15,000 degrees. And Jim was pointing out that energy is sent up basically out from the sun into the corona by magnetic forces, traveling up these arches. You remember we talked about sunspots as well, and how sunspots come along in pairs, and one of the pair will usually be the north magnetic pole, and the other pair will be a south magnetic pole. And they would be linked by a loop. Well, this is the loop in profile. If you were to actually be able to look down on the loop, in other words, if the loop, instead of being at the edge of the sun, was somewhere in the middle of the sun, then we'd be looking down at a dark streak. And that dark streak is called a filament. Jim pointed that out to us. They occur all over the sun when you've got lots of activity, which we don't have right now. But the reason they're dark is because they're cooler. So here you've got this real dichotomy and paradox. Scientists today think that the magnetic energy creeping up the limbs of the arch here from either side towards the top, that they're actually taking energy up to then release it into the chromosphere and heat the chromosphere up. But it turns out that the top of that arch is actually cooler than the lower parts of the arch. So what you actually have to do here is you have to think about energy and the concentration of energy. And it's the concentration of energy that actually gives you temperature. Or, sorry, it gives you heat. It's the kinetic movement of molecules and the speed at which they move around and bounce off each other that gives you the temperature. So as Jim was pointing out, you've got a corona at 1,000,000 degrees centigrade, but the atoms, or the ions in fact, because they're ionized, are so thinly spread through space that there's actually major gaps with no ions in them. And so you've got these ions moving around very fast because they've got lots of energy, but since they're not concentrated, you don't actually have lots of heat, but you do have a high temperature if you follow all of that. So the thing is that the various hypotheses that the physicists and astrophysicists have for explaining the heating up of the corona involves these structures here, but there are several things. There's the actual magnetic energy going up around the edges of the arch here towards the top. There's also the vibration of the lines of magnetic force, which Jim explained to us. But there's also a rubbing. This is going to sound very strange. There's a rubbing of the magnetic lines of force, rather like friction. If you were to take two pieces of wood and rub them together, they will warm up. This is how people created fire a long time ago. Well, believe it or not, magnetic lines which rub up against each other also create or have a phenomenon of friction, which creates heat. So there's all kinds of things here contributing, plus the structures, the fibrils, sometimes also called spicules, that Jim was referring to. And again, these things are dancing and rubbing up against each other, and again, producing this frictional heat. I don't think anybody has a full story for this, but these structures here, which you see, this kind of phenomenon, this arch, is very much key to it. A couple of years ago, I was making a time-lapse movie. Jim explained time-lapse movies, where you take images maybe every 30 seconds. It might be a 10 millisecond frame. And you take them for several hours, and then you run them all together in a special piece of software to make a time-lapse movie. And I was watching one of these arches, not expecting it to do much more than this one's doing. It's not doing very much. And then all of a sudden, it began to grow really, really quickly. It grew in about 25 minutes to a huge spike, the size of maybe 20 times the diameter of that arch. Now, as Jim had pointed out, there's no way that gas was actually traveling that quickly, because that's going faster than the speed of light practically. But or at least it's going at speeds clearly close to the speed of light. But what was happening was that the gas that is out there was becoming energized. As energy was being transferred out into the gases immediately above the arch. And so the visible arch grew longer and longer and longer. And it then collapsed. All of this within the 25-minute time frame. And as it collapsed because it actually cooled down. And as it cooled down, the gravity of the sun managed to pull the glowing remnants of the gas back towards the sun. And that's a phenomenon known as coronal rain. In other words, it rains on the sun, but it's not raining water. It's raining hydrogen plasma that's cooling, and as it cools, it starts to get denser, heavier, if you will, and therefore the gravity of the sun is able to pull it down all the more easily. I'm just looking out the window there, and I see that the clouds are coming in. I can see the deterioration of my arch there. I know I've only been talking for about 5 minutes, but if Boyan's going to have anything to say, this might be the time for him to jump in if he wants to. Dave, any idea of whether Boyan would want to jump in here?
Sure, I can just briefly talk about my view, and I see clouds rolling across my image as well. So
let me stop sharing there and let you in.
Is that coming through all right?
You're good to go.
Awesome. So Simon covered everything quite eloquently. We have a similar view here of the sun with my setup. Actually, let me perhaps show what that looks like. Let's see, right here. Okay, now I guess we can see both. So this is my setup currently in the backyard. It's a similar setup to Simon's in the sense that we have a hydrogen alpha scope in the mix. If you remember what I spoke about this morning, we have different types of etalons that are providing the images that we see today. So Simon's etalon is a tilt-tuned etalon. I'm pretty sure about that actually. And what that, with those two mirrors that I spoke about this morning, the two mirrors are parallel to each other. However, they can be tilted slightly, which changes how much interference occurs. If I can just draw your attention actually to the picture of the sun right here and how quickly the picture is degrading. There it goes. So right now, a bunch of clouds are actually passing over the sun. And with the high gain that we have right now, that is starting to blow out the picture. So this may be the last views we get for the day before the clouds completely envelop the sun. Unfortunately, with our telescopes, we are bound to the weather, and even a very thin layer of clouds. A couple of people have asked me today, well, today's a beautiful day. It's beautiful and sunny. We can go outside. And yes, today is beautiful and sunny. However, it is not a great day for astronomy for various reasons. The clouds, the atmosphere is quite turbulent, as we saw. So I keep pushing down the gain in order to preserve the image as much as I can. However, we're slowly starting to get covered by clouds here. Let me turn down the gain a bit. No. Let's bump this up a bit. There we go. So back on the telescope side of things here, Simon's Etalon, which is what does all the filtering to get this image, his is tilt tuned. So the two parallel plates are parallel, and they can slightly be adjusted relative to each other in order to provide destructive interference and filter out all of the light except for the red light. On this scope right here, which I will zoom. So on this type of telescope, the sunlight travels through the front of the telescope. It goes down and hits this Etalon system here, which is encapsulated in this red ring here. So this type of Etalon system has what is called a piston right here. And before you begin your observing session, you take out this piston and then you slowly start screwing it in. That piston actually raises the pressure inside of this chamber, and that also changes how the two parallel plates function relative to each other. And my type of tuning system uses pressure as opposed to Simon's, who uses tilt tuning. I believe Jim's system actually uses heat. I'm not sure what his equipment is exactly, but I believe it's the same two parallel plates that use heating, and the heating changes the amount of destructive interference that happens in that Etalon system. So as I've been talking, you've perhaps been looking at the sun here as well on the right-hand side. And what's interesting is sometimes the picture is very bright, sometimes the picture is very dull, if you will, and that is just actually the amount of cloud cover or just any sort of pollution that lies between my telescope, which is on the ground, and the top of the atmosphere, which is where all that is being, sorry, just changing the gain. So as you can see, this is an ever-ending battle if we're doing live astronomy like this on changing the gain settings so that we can get a pleasing image. The sun's been spoken about a lot. I want to make sure that this is perhaps interactive. Are there any questions from anyone? If they have general questions about just the sun or science or astronomy, I'd be more happy to field those as well. Please type those in the Q&A chat and I'll keep talking on about the sun until we have something else. So right now,
Boyan,
yes.
Jim just confirmed that he has tilt tuned like Simon's.
He does, okay.
Yeah.
So I don't think, I'm not sure what the other astronomers have in the group, but it could be a heated system. What would I like to talk about? So here's an interesting scientific occurrence. So as you can see, the image is dimming right now even more, which means there's more junk in the atmosphere, pollution or clouds that are constantly moving within the field of view and out, which is causing us to constantly have to adapt our cameras. So I read about this recently. It's an interesting story, but I believe in the late 1980s, there was a volcano that blew up somewhere in Southeast Asia. And that volcano released a lot of particulate into the atmosphere, which got carried around the world. And amongst the first people who noticed the effect that this had on our atmosphere were amateur astronomers, because we set up our cameras and all things staying the same telescope with the same camera in the same location should more or less on any given night use the same camera settings. So that's exposure here at 0.3 milliseconds and a gain of 175. However, after this big volcano explosion, it released a bunch of ash into the atmosphere, which circled the globe. And a lot of amateur astronomers noticed this because they had to change their gain settings on their cameras to counteract the dimming effect of said ash in the atmosphere.
Okay, boy, we have a bunch of questions here for you.
Awesome.
First question is, what is the camera that you have on your telescope?
It is a very cheap $40 Celestron Nexstar black and white burst camera, USB 2.0, very, very basic.
Okay. Somebody's asking about, are we going to learn about the moon? And yes, we are going to be talking about that a little bit later on. Next question is, what causes Newton rings when imaging the sun?
That is a good question, and off the top of my head, I'm actually not sure. Simon, would you like to jump in for that one?
Yeah, sure. Newton rings are an annoying phenomenon when they happen. It's essentially what is happening is that with any sheet of glass, you have two surfaces. You've got a surface on one side and a surface on the other. If those two surfaces are not absolutely parallel, then light passing through that sheet of glass, and remember, this could be a sheet of glass, a filter, it could be in the telescope, it could be in the camera, it will then change very slightly the wavelength of the light coming through from one side compared with the light going out the other side. And so you get this interference where you get some wavelengths are constructively interfering and they form the bright rings. They're actually circular, but the size of the circles it depends on the telescope, on the camera, on the piece of glass that's causing the problem. Sometimes that circle can be maybe just a few centimeters across. And so you'll actually see rings in the field of view. But sometimes the circle is actually of the scale of meters, which means that the segment of the rings that you see looks dead straight. The answer to actually solving the problem of these Newtonian rings is to actually introduce a very small piece of equipment that very slightly tilts the camera. We're talking a fraction of a degree here. And what it does, by tilting the camera in the right direction by the right amount, you compensate for that constructive interference on the part of the Newton rings, and it clears up.
Thank you. Next question. Can somebody explain solar wind?
Sure, I can grab that.
Go for it, Juan.
So part of the sun's process is just the constant movement and, yes, the movement of particles throughout the chromosphere, which we spoke about earlier. So that is the medium layer, if you will, on the sun between the corona and the photosphere. Throughout that, there are charged particles which are constantly being ejected from the sun directly outward. So these are actual, excuse me, physical particles that are moving away from the sun at up to 800 kilometers per second. And this is a constant stream of particles that is being ejected out from the sun. These particles can travel through space and eventually interact with the Earth's atmosphere, causing northern lights. Also, the solar wind and these particles also keeps traveling, and there are certain space missions that have tried to leverage this using solar sails. So if you have a satellite which is up in space and you deploy an area like a sail, you can actually harvest the energy of these particles that are emanating from the sun and use that to physically move your satellite that is in space.
Okay, that's it for the questions so far.
Okay. What else can we talk about? I can talk a bit more about the setup here. So this little virtual hand controller is actually a physical or virtual representation of my physical hand controller for the telescope. So if you see over here, it's kind of dangling right here by the telescope, that is hooked up directly into the laptop, which is both doing the imaging on the camera as well as controlling the telescope. So on this type of equatorial mount here, it's called equatorial because it has to be aligned with the latitude that you are actually on the Earth. So this front tripod leg is actually pointing due north in my backyard. And we have to do that in such a way because all the objects in the sky follow a predetermined pattern based on how the Earth is moving through space. When you have an equatorial mount, you can align your scope with the sky and your location on Earth such that you only need to move one of the motors to track an object through the sky. Now, as you've been probably seeing here with the sun, every single once in a while I have to hit a couple buttons to move it back into the field of view. And the reason for that is because during the day, we still need to have this mount pointing directly north. However, in the middle of the day, I don't have the North Star to actually point that telescope at directly. So I had to use a compass. The compass isn't the greatest, so it was difficult to actually just point that directly north. So you kind of just eyeball it, you put it down as close as you can to due north. Your mount also has to be perfectly level, or as level as you can make it on the grass. And then you tell the telescope actually through this hand controller, it's like, hey, today is May 2nd. It is 1:21 p.m. I live in Ottawa, Canada. And then the telescope hand controller does a bunch of math and knows exactly where the sun or any other object in the sky is. And then we can use the hand controller and just tell it, hey, I would like to look at the sun. And the telescope moves over to the object. I see some questions here. Did we want to address those?
Yep, okay. So what are the charged particles made of? And when you say that, do you mean they would be isotopic elements, or are they actually solid compounds?
That is a good question. So my understanding, and I'll let Simon supplement my answer, but the charged particles we're talking about are actual atoms of hydrogen or helium or any of the other elements that are making it to the surface, and those are actually moving out. Simon? You had it for a second. You're still muted. There you go.
There we go. Okay. For some reason, I've got you terribly small on my screen. That's okay. Okay, I see it. Yeah, Boyan's quite right. What these things are, they're charged particles. So they actually have to be atoms that have lost electrons. Principally, they're going to be hydrogen and helium, because the sun is essentially hydrogen, and through its nuclear reactor, it's trying to convert that into helium, and that's what's giving us the heat. And so this is also what the sun is mostly made of, and that's what's mostly in the solar wind. However, there are also traces of things like oxygen, carbon, nitrogen, but the sun is not a great producer of those compounds, of those elements. But the important thing is that what's what's traveling in the solar wind, they are charged atoms. In other words, ions.
Okay, we have another question here. How far does the sun's gravitational field reach? Is it up to the heliopause or beyond the Oort cloud, or still beyond that?
Do you want to do that one, Boyan?
That's a good question. We have some really good questions, actually.
The answer to that one's very simple. It actually goes on and on and on. It just gets weaker and weaker and weaker. So the sun can actually be gravitationally interacting with other stars.
Okay. Next one was, I thought a solar sail used photon pressure as opposed to the solar wind.
And Mary, I believe you are actually right. It is photon or electromagnetic radiation pressure, not physical particles. However, physical particles can still affect these satellites that are up in space. I know when we have satellites that are higher up in orbit, they are affected by these particles physically as well.
Okay, the next one is for Boyan. What brand is your mount? How do you sight in it? What accuracy does it provide for tracking? And how long does it take you before you need to adjust it?
Excellent question. So the brand of mount is a Celestron CGEM mount. I think the payload capacity is about 30 or 40 pounds. To sight through it, if I'm understanding your question correctly, for polar sighting, there's a little cutout right here, which is bored through the entire length of this part of the mount. Do I have a better picture of that? Hold on. So this hole right here is where the polar scope would go, and you would undo this backing right here, and you would use that along with your latitude and balancing the scope and making it level to locate the North Star through a polar scope in here. Now this is really only used when you want to do very precise astrophotography and doing long exposures of minutes or hours. Your question was, how well does it track, or how often does it need to be adjusted? And that's entirely a function of how good of a job I do at the beginning. Today, it was a very rough job. I literally placed it down. It's not perfectly level simply because the grass is uneven or the ground is uneven. So for visual astronomy, like we're doing right now, the little parasitic sort of adjustments I have to make every couple minutes that you see here is a trade-off I was willing to make. However, for astrophotography, we would probably want to spend a good 20 minutes polar aligning, and then on top of that, the controller here, the controller has intelligence in it to calibrate the scope even further. So this physical part of placing the mount down is important. However, to supplement that, the hand controller will point, to example, to a star. It will say, hey, you should be looking at Sirius right now. And then you look through the scope and you realize Sirius is maybe 2 or 3 fields of view away. So you move the scope over and you tell the scope, hey, actually I'm at this star right now. And then the controller does some funky math to compensate for the fact that you are actually not perfectly polar aligned or perfectly level on the ground.
Okay, next question from Dennis. Is linking a computer to a telescope drive complicated, and any comments on the best approach?
So for obvious reasons, this is not my permanent setup with a chair and my laptop right there. To be honest, this is the first time I've ever done live streaming like this. It's working out okay, but in general, I just enjoy doing visual observing. If you have the ability to do a permanent setup, similar to gyms, where you can have this type of equipment just sitting outside and you uncover it whenever you want to use it, that is an awesome option. I know Simon, I believe, runs cables directly into his house as well, so that he can project some of the stuff directly onto the TV, I think bypassing, but you need a computer at some point in the stage to interact with the mount, to interact with the camera as well.
How complicated is it to set up?
To be honest, again, I have not done this ever, and it took me 10 minutes today. I had all the software already installed, so everything is through USB. Everything gets detected very easily. This is the video capture software right here, which detects the camera immediately. The only thing you really had to do here was focus the telescope, and then the rest I'm doing actually from my basement, as you can see, remote desktop into my laptop, and I can control everything from there. So it was actually a lot longer to haul out the telescope, balance it with the counterweights, haul out the giant 30-pound tube, get everything level. That took probably a good 40 minutes. The electronics part took maybe 10 minutes.
Okay, super. So this is a question for any of the panelists. It was mentioned earlier that the Earth's moon is slowly moving away from the Earth. Can this have an impact on Earth at all?
Well, I'll jump in on that one. It is doing that. If you go back 400 million years in Earth history, some of the early corals are present as fossils. And one of the wonderful things about corals is that they actually deposit their shells, their skeletons, according to the tides. And so by slicing these corals open and putting them under the microscope, you can actually count how many days there were in a year. And it turns out that about 400 million years ago, the days were a lot shorter. There were a lot more days, more in the order of about 400 days a year rather than 365. And the reason that the Earth is slowing down is because the moon is tugging on it. The Earth is tugged on by the moon, and that creates the tides. Everyone knows what tides are when they're thinking about water. But it turns out that there are also tides in rocks. In other words, the moon pulling on the rocks of the Earth, whether it's the sea floor, the ocean floor, or whether it's the continents that we actually live on, those rocks rise and fall, something of the order of maybe a few meters every day as the Earth spins underneath the moon. So that means that the Earth actually isn't a sphere, it's a sphere with a bulge on it. Well, it turns out the Earth is pulling on the moon. And the moon, of course, doesn't have any water for tides, but it does have rock tides. So the moon also has the shape of a sphere with a bulge on it due to the gravity effect of the Earth. So here you've got these two spherical bodies with a bulge spinning underneath and around each other. And it's the bulges that are actually pulling on each other. If the moon is ahead of the Earth's bulge, it pulls the bulge forward. If the moon is behind the Earth's bulge, it drags it backwards. So the overall effect of all of this is that the moon slows the Earth's rotation, and the Earth manages to pull angular momentum. The Earth adjusts the angular momentum in the Earth-Moon system such that the moon actually starts drifting outwards. And so the moon is on its way out. It's moving outwards at about 4 centimeters a year. And we can calculate back to see when the moon probably started on its journey. Well, it turns out that if you do that, turns out that the moon must have been actually right next door to the Earth only about 1.5 billion years ago, which is nonsensical because we know the moon is 4.5 billion years old. So that means that the moon has not always moved away from the Earth at the same speed. It must have fluctuated in speed, sometimes faster, sometimes slower. So the bottom line is, yes, we do know the moon is going around the Earth and it is affecting the Earth, but we don't know the history of that effect in any detail.
Okay, thank you, Simon. Another question?
Wanted to just add something to that, just an interesting tidbit, but yes, the moon is moving away from the Earth. In a couple million years, it will have moved sufficiently far away such that a total solar eclipse will not be as enjoyable because the moon will actually be further away from the Earth. It will not perfectly cover the disk of the sun, and we won't have a perfect solar eclipse. We'll still see the edge of the sun, and it'll be a very different view than we're used to today.
Okay, thank you. Another question. Once Voyager 2 reaches interstellar zone, will it be under the influence of Proxima Centauri gravitational polar force?
So mathematically, the force of gravity is existing everywhere. So even there is a force of gravity between my body and Voyager 2 right now, however insignificant. It's primarily a function of distance for gravity. So even once it reaches the interstellar zone, which could be about a light year away, depending on how you define interstellar, the primary gravitational force on that Voyager probe will still be our sun. However, once it reaches closer to Proxima Centauri, then the primary dominant gravitational force will be from that star.